too. I mean, every year we have to spend a lot of money to restore that comfort. So it's very important that while we are designing a building, we should keep the local environment in mind, and also the thermal comfort requirement of the people in mind, and these two factors will govern our building design and should govern our building design. Comfort plays an important role in sustainability also. Comfort decisions can have substantial health, energy, and resource consumption implications, because we know if we move into the house and if it is not comfortable, then we will do certain changes in the house to make ourselves comfortable. And since we cannot do anything about the external facade, so what we do, we install air conditionings, because this is the only option we are left with. And what will happen then if we install more air conditioning? We will use more energy, and more energy use means, since this energy is primarily sourced from conventional fossil fuels, so it will lead to different kinds of pollution, air and environment pollution, and then ultimately it will lead to global warming. And as global warming, there will be increase in temperature. As temperature increase, we will use more air conditioning, and this is the vicious cycle, and this will go on, and we want to break this cycle. So to break this cycle, the only solution we have is to design buildings that respects existing environmental conditions, as well as respects the occupants thermal comfort requirements. So what is the challenges in thermal comfort study? The challenge is lies in the definition itself, because as defined by ASRE, the thermal comfort is that condition of mind which expresses satisfaction with thermal environment. So it says that a subject in the environment is a passive recipient, and its inherent capability of adaptation and adaptive actions are ignored in large extent. So here, whatever environment is given to the subject, it accepts it. So it is a passive subject, is a passive recipient. But when this definition is tested in the field, large number of anomalies reported, and then the concept of adaptive thermal comfort came into the picture, and it is included in the ASRE standard also. And it is defined as, if a change produces discomfort, people react in a way which tend to restore their comfort. So here, this definition tells that an occupant is an active ingredient of the environment, and it always takes those actions which restores its comfort. So that is very much obvious if we look ourselves in this, and keep ourselves in this context. So this definition seems to be more appropriate. And what is this leads to? Because these definitions are subjective, they have large variations physiologically and psychologically from person to person. So the data which we collect, they have a large scope. And now what we have to do, we have a daunting task, because we have to converge all the data with some statistical tools, so that we can give environmental variable some environmental variable in a range that defines the comfort. Like we have to give temperature range, we have to give humidity range, we have to give air velocity range in the built environment. So in this range, an occupant will be comfortable. And this is this also it's built environment dependent. like what is the functionality of the building, whether it is a recreational hall, or it is a residential building, or it is a hospital, or it's a school. These values will change. And also it has some seasonal implications also. So we will see in the later part of my presentation uh, these variations. So what we'll do when we go for field surveys, we record the thermal sensation data. So we'll those data will see, like, it says that now how the occupant is feeling, and also what is its preferences now. So two nows are covered. One now deals with the present thermal sensation, and one now deals with what is the occupant's preference, what he prefers. So these are very important things, so we capture in our field surveys. So in this context, since we know that the thermal comfort has a lot of energy implications, so let's see the picture of the world primary energy consumption. So in this we see that residential sector consumes about 21% of the primary energy. Industry is and transport, they are the highest consumers. But overall, if we see this picture, buildings are responsible for more than 40% of the world primary energy consumptions, because we see that 8% it's responsible for commercial and public services. There also some buildings are involved. Here in transport also some buildings are involved. In industry also there are buildings involved. So this data is not segregated specifically, but if we take those things from these three sectors, the share of building energy consumption will go beyond 40%. And this is a huge. Now, in the context of India, more than 93% of the world primary energy is obtained from conventional fossil fuels. In fiscal year 2020, 75% of the India's electricity production is achieved through coal thermal power plants. And see this from where our energy is sourced from. India total CO2 emission in 2020 is about 2.63 billion tons, and out of which the contribution from combustion of coal is 1.68 billion tons, nearly 64%. And India has proven coal reserves for about 111 years. And also, we know that substitution, like, if we want to move to cleaner energy, it is financially intensive. So the substitution to clean energy, it will take a lot of money, and most of the in countries, they are not ready for that. And the similar is the case for India. So for another 40-50 years, coal is not going to be replaced. So that is a worrisome sign if we think about global warming. So this is about final energy consumption in different sectors of India. So you see this residential sector, we see just 11%. But again, here there is no distinct segregation of the data. So here also, if we take the overall picture, it will come close to 40%. It follows the world trend. But even if we see this picture, we can realize that if we carry out a small intervention by using digital technologies, then it can bring significant improvement in efficiency of the supply demand system and industry itself. So uh, that is my intention, is to say that Like, now we have a lot of digital technologies. So if we can use that technologies to improve this, efficiency, then there, we don't have to install that much of thermal power plants. So we can get rid of subsequent CO2 emissions. And this is the overall energy consumption in the building, and it's a breakup. So we know that if uh, some amount of energy is supplied to the building, then 60% of it goes to the air conditioning, 20% of it goes to the lightings, and 15% of it goes to the ventilation. So this is a worrisome, again, this is a worrisome trend, because 60% is going to HVAC. So we want to reduce this portion, because this is, HVAC systems are highly energy intensive. So our main goal is to reduce this section. Now I'll talk about thermal comfort research, new dimensions and direction. So we have crossed 3 industrial revolutions, and now we are in 4th industrial revolution, and it is called digital age. So in first industrial revolution, it happened in 18th century, and the main key technology is the steam engine based in industrialization. And main factor in driving the economy is the steam engine based technology. So we have devised steam engine, and we are using that for industrial revolutions. So main driving factor is steam generation. And here also what we are using for steam, producing steam, is coal mainly. In second industrial revolution, the key industrial technology is electricity based mass production, assembly line concept. And main driving factor of the economy was oil and steam engine based technology. By that time, in the 19th century, oil was discovered, and then we have just started using oil. And in third industrial revolution, the key industrial technology was computer and internet based knowledge concept, and main driving factor of the economy was oil. And so in 20th century, we can say it's a oil economy. And the fourth industrial revolution, which is presently going on, the key industrial technology is big data, AI, IoT, hyperconnectivity, etc. So we see that main thing is the digitization. And the factor driving the economy is oil plus renewables plus hybrid technology and hydrogen. So gradually we are moving towards clean technology, and we are trying to get rid of fossil fuel based energy sources, but still it is going to take time. But what we can do, that we can use this digital technologies to improve the efficiency of the system, and that way we can make the renewables, hybrid technology and hydrogen based systems more reliable, and we can increase their availability. And on the other hand, we will, since the reliability of this technologies will increase, we can reduce our dependency on fossil fuel based energy sources. These are the key components of the industrial revolution 4. They are cloud computing, augmented reality, big data, autonomous robots, additive manufacturing, simulations, system integration, blockchain, cybersecurity, Internet of Things. So these are some of the technologies that are being used now. So since this is, here we are talking about buildings, So buildings are very much, it is related with people, their well-being. It provides some kind of sense of security. So it is very much integral part of UN Sustainable Development Goals. So if you see the Sustainable Goals 3, 7, 11, and 13, they are directly and indirectly related to thermal comfort studies. And we can say that they are the extended domains of thermal comfort study. The literature published in scientific journals do show some promising and interesting results. But still, there is a big question, and we don't know how this will play out in coming years in the context of IR4. So let's talk about Sustainable Goal 3, good health and well-being. This is said to be the main focus of thermal comfort studies. Thermal comfort studies are done in different built environments such as residential building, offices, commercial buildings, hospitals, and classrooms. Until most recently, most of the data collections were done by employing field surveys, which is surrounded by a lot of constraints and uncertainties. Thus, accuracy of thermal comfort parameters evaluated is greatly impacted by accuracy of collected data. To overcome above constraints and uncertainties, various solutions like IoT, digital twins, etc., for recording of parameters with minimal human involvement were devised and effectively used. Use of IoT and digital twins has increased the accessibility, accuracy, and amount of data collection. This has provided the capability for online and live thermal comfort assessment, thus used as feedback instruction to control HVAC systems. So since these are the uh, live feedback mechanism, so I will just discuss with you with one of the examples. So Professor Richard Didier in Sydney, they were studying on this, and they took a 5-story office building with 500, more than 500 people sitting in this office. So they started monitoring with the online systems, and what they found is that when the people enters the office at 9 a.m., they increase the HBAC. So HBAC set point. So they put it at 22 for cooling, and gradually when the people, because people they will enter the office from around 8:45 to 9:30. So after that, they gradually increase the set point of cooling from 22 to 26 degree. So at noon, entire HBAC system was running at 26 degree, because this was the logic that since people have entered the office building and now they're not leaving till 5 p.m. and they have spent considerable amount of time, almost more than 1 hour, and now they get adjusted to the surrounding environment, so they don't need that amount of cooling. And they, in their surveys, they found that if the building is operated at 22 degrees at 22 degree cooling set point, people, most of the people, they felt cold. Excessive cooling, they reported there is excessive cooling, and cooling, they reported cooling discomfort around the noon. So they devised this, and then they run this thing until 4 p.m. 4 p.m. and after that they gradually started shutting down, because the people, some people they will leave early, and some, and most of the people they will leave by 5. So on analyzing the data, they found that they are saving almost 30 to 35% of energy requirement. So they are reducing the cooling energy requirement by 30 to 35%. and this is a huge saving. So, and this is now studied more and more, and the people are trying to develop some kind of technology so that they can do live monitoring and they control the HVAC system, you know, more frequently. Now, thermal comfort in the context of sustainable goals 7, affordable and clean energy. This is indirectly associated with thermal comfort studies, and we can say it's an extension. It is widely accepted that occupant behavior influences energy use and pattern in a building. Building integrated PV, ground source heat pump, district heating, solar domestic hot water system, etc. are some examples of clean and affordable energy. Studies were carried out to analyze the impact of above clean energy technologies on overall thermal comfort of the occupants. Zero energy and net zero energy buildings also revolve around this theme. Use of IoT and digital twins has increased the accessibility, accuracy, and amount of data collection. Now, thermal comfort study in the context of Sustainable Goal 11, Sustainable Cities and Communities. This is the theme that is directly as well as indirectly associated with thermal comfort studies. It is widely accepted that occupant behavior influences energy use and pattern in a building. We know that energy use is one of the prime factor in assessment of buildings. Also, clean and affordable energy supply is an integral part of sustainable cities and communities. There are very few studies done that establishes a link between thermal comfort and sustainable cities and communities and economic aspects of it. So we need more study in this regard. Thermal comfort in the context of Sustainable Goal 13, climate action. Under this theme, again, the energy intensity of building comes into picture. It is well known that building running energy consumption throughout its life is way higher compared to the construction. It is widely accepted that occupants' behavior influences energy use and pattern in a building. Building construction is also financially very intensive, so adoption of advanced and energy efficient technologies are very slow. Above factors made buildings as one of the highest CO2 emitters, directly and indirectly. So most countries in the world have green rating system for building energy efficiency and performance. In the context of climate change and long life of buildings, how the buildings will behave for future climates along with financial implications has created a lot of interest regarding occupants well-being and policy point of view. In last 5 years, numerous studies were carried out on this aspect, and this is still a very hot topic where a lot of research is going on, and mainly they are based simulation based studies. And future of thermal comfort research. So the thermal comfort research is again moving towards personalized thermal comfort in offices and other built environments for higher productivity, linking occupant behavior in building simulations as it impacts energy consumption. Impact of climate change and changing weather patterns on present and future thermal comfort requirements of occupants and their behavior. Impact of climate change and changing weather patterns on human well-being. Building energy simulation and building model calibration procedures are not standardized. So this created a problem to evaluate results. So this is the biggest issue because all these studies are mainly simulation based, and somewhere we need to calibrate the building model with the base case where we carried out some measurements, and this calibration process is not standardized. So we are trying to publish some papers. So maybe in few 2 or 3 months it will come. So here There we have put emphasis on how to calibrate a building model, and that the same model again, once calibrated, will be used for running simulations for different cases for future climates. Use of IR4 technologies in thermal comfort assessment and its implications in the domains of sustainable goals 3, 7, 11, and 13, and in the context of built environment. So uh, in this, I have listed where this thermal comfort research is going. So we will see a lot of papers coming in this direction in future. Now I'll talk about my experience of research in different built environments. So first I will discuss the research that I carried out in traditional residential buildings of Northeast India. So when I started my study on this traditional buildings, and then I carried out literature survey and found that the climate of Northeast India is not classified in the context of building. So before starting my work on the buildings, I have to analyze the climatic data, long-term climatic data of Northeast, and then I classified the Northeast India in different climatic zones. So these are the places where from where the data is collected. So it's our temperature profile, humidity profile, precipitation profile, and altitude. And after analyzing the data, we come to know that there exist three distinct climatic zones, like a warm and humid, cool and humid, cold and cloudy climate zone. And one is highland climate zone, which is just snow-clad mountains throughout the year. The mountains are snow-clad, so there is a very few people reside there. But mainly, there's three bioclimatic zones. So these are the specific information about the classified bioclimatic zones. So we have like summer and winter maximum and minimum temperatures, then humidity range, rainfall range, sky condition, wind direction, and vegetation. We also used to estimate the passive design strategies potential in these three climatic zones. So these are the passive design strategies potential. Now, once the bioclimatic classification is done, so what I did, it should be supported, and it should be supported by the features uh, that I will find that will be found in the existing traditional architecture that are more than 70 to 80 years old. So what I did, that I carried out surveys and to list out the solar passive features in these buildings, and whether just to know whether these passive features that I will find in a specific climatic zones, are they in line with my bioclimatic classification. So in this way, it's just a validation of my bioclimatic classification. So I carried out more than 7 surveys in all these three climatic zones and covered more than 70 buildings. Some of the features are listed here. So this is about warm and humid climate. So here we see that there are a lot of features that promotes the ventilation. Like, there are chimneys are available. There is an opening in the false ceiling, so it just enhances the air circulation. The size of windows, doors, they are very large. These are some ventilation techniques that I found in warm and humid climate. This is the shading techniques in warm and humid climate. These are in line with my bioclimatic classification. These are the architecture of cold and cloudy climate. So here we see, this is a picture from Shillong, and you see this compactness of the house, the size of windows and doors, and they have used locally available material, stone blocks, to build the house. The walls are very thick. Also, they have a heating place in the living room. Then I carried out a thermal performance study in these houses. So I selected 3 houses, like one in each climatic zone, and I monitored it for 1 year. So this is the house that I selected to monitor. This is the first house is uh, house in warm and humid climate. This is called Assam type. It's very popular. One is in cool and humid climate, that is in Imphal. This type of houses are also very popular. And one is in cold and cloudy climate in Cherrapunji that I monitored for 1 year. These are some of the statistics about how many subjects they participated in my survey, how many houses I covered, what is the age, how many male, female. So I found that the neutral temperature, it goes on decreasing from warm and humid climate to cold and cloudy climate. So for warm and humid climate, the neutral temperature is around 26 degree, cool and humid climate it is 24 degree, and cold and cloudy climate it is 22 degree. So there is a gradual decrease in the neutral temperature, and neutral temperature is defined as the temperature at which the occupants did not report any discomfort. They say that they are comfortable, thermally comfortable. And I also reported the thermal comfort range, because neutral temperature is it's good. It gives the information, but when we give this information, then it is very particular information, and then based on this, a building designer or an architect find it very difficult to design a building for specifically that. So there has to be a range of temperature. If we give a range of temperature, then it becomes easy for an architect or an building engineer to integrate some of the solar passive features, so that if there is a fluctuation, he can manage with in that range. So I found that for warm and humid climate, the comfort temperature is varies from 22.8 degree to 29.1 degree. So it is throughout the year, this is the range of the comfort temperature. And then for Imphal, it is in between 21.1 to 27.6. And for Cherrapunji, it's Cherrapunji means it's cold and cloudy climate. It varies from 18.9 degree to 26.7. So in all this climatic zones, almost 7.5 degree range is there. So based on this range, it gives the architects and the building engineers an option to integrate climate oriented features in this building to restore comfort, and thus they can reduce the energy use in the building. So I in this research I also got an honor to write a paper with Professor Gioni, who is a very renowned uh, scientist in this area. So he has given a lot of tools, like bioclimatic tools, and these are very helpful for architects who are designing climate oriented buildings. So with him I learned this technique and I developed the predictive formula to predict indoor temperatures of the buildings if we know the outdoor thermal conditions, because it's not possible always to go and monitor all the houses. So if we can do the monitoring of the representative house, then we can use this technique to predict what will be the temperature in that house in particular season. So this is the technique. And then I also tried to integrate occupant behavior in building energy simulation. So this is the house that I monitored for in warm and humid climate. So I used Transys to model this building. So here during the survey, I found that the occupants they are opening and closing the window at particular time, and then I recorded the corresponding temperature, and then I devised this strategy. So the control strategy one that I got from the surveys, and then the control strategy two that I assumed, and now I try to see what is the impact of these two control strategies of opening and closing windows on the indoor temperature of the building. So after analyzing the data, I found that control strategy one is very effective. The occupants are, they are using the operation of windows wisely to enhance the comfort in the building. So uh, employing the strategy one, there is a reduction of temperature up to 2.5 degrees in the building. But on the other hand, control strategy two, it is leading to temperature buildup. So you'll see there is a buildup up to 4 degrees in the summer month, and this is the simulation. On the x-axis, you see the number of hours in a year, and in the center from 2921 hours to around 5841 hours. This is the peak summer season. It's starting from May end to around July and August middle. So you see that there is a temperature buildup for strategy two, which I devised, and strategy one, there is a reduction in the temperature that I got from the surveys. Same for the next figure. And also, since the previous analysis is just giving the reduction in temperature, but I want to know what is impact on monthly comfort duration. So what I did is that I extracted the data that lies between the comfort range. That what I have presented in the previous slide, and that this is the range of comfort. So I just extracted the number of hours from the simulation results where the temperature of the indoor temperature lies in that range. So here again, I found that for strategy one, there is a lot of improvement in the comfort duration in summer season. Same is for zone 2. Also, I studied, the effect of cool roof, and this study was suggested by Professor N.K. Bansal. So now he is no more, but he suggested me that I want you to study this the effect of cool roof, because now a lot of reflective white paints are coming, and there are a lot of industries, they are promoting it. So I want to see the effect. Can you do this for me? So I said, okay, sir, I will do the simulation. So I did it. I did the simulations and I showed him the results. So he was very happy to see that. So we had a very long discussions on this. So some of the results I will show, and I also presented this in an international conference. So for this, I took a sample building. This is the dimensions it is shown here, and on the bottom left hand side you see the roof configurations that I used for this in this study. So there is a roof slab, and above that I put a white paint, and also I put for another case I put a roof slab and then insulation on the top, and just to see what is the impact. And these are the thermophysical properties of the building materials that I give as input to this model. So in indoor temperature swing in composite climate. So this so I just plotted the differential. So I set subtracted from base case and cool roof. So you see that there is a reduction in the temperature and the summer month. So about 3 degrees. 3 degrees there is a reduction, and this is the hues. Exactly 3 degree reduction means just by employing a reflective coating on the top of the roof. It's the hues saving, and same is the hot and this is for composite climate. The left top figure is for composite climate, and right top is for hot and dry climate. So I consider two climate zones, and in both the cases, in summer month there is a reduction of maximum 3.5 degrees, and in summer it's about 2.5 degrees. So this is the hues. So again we see that it has also a positive impact on the number of comfortable hours in composite climate and hot and dry climate. They improves this, like in a comfortable hours it improves in summer month. This is about the roof inside surface temperature in summer season, and you see that in cool roof there's a lot of impact, like there is a drastic decrease in the inside surface temperature. Also the heat flux, and you can see this the crossing, like with the insulation and cool roof, and roof with no coating and no insulation, like in the base case. So huge heat flux, and then it is with the white coating, uh, white paint coating, it is restricted to 20 watt per meter square. And also it's like its peaks, so its peak is also shifted towards evening. Now after that since I carried out these and studies, and then as I told you in the in the definition itself, there is a discrepancy, like uh, when we analyze the data based on these two definitions. So what to do with that? So there is a need to develop a corrective term that is called adaptive coefficient. So to remove that discrepancy, I used that data and calculated this, the adaptive coefficient that is added to the definition one to bring the result close to the field study. So this is the adaptive thermal comfort model, how it and occupants interact and how its behavior affects its sensation. And this is the formula where lambda is the adaptive coefficient, PMV is the predictive mean vote. The figure in the green text, you see that this they are the adaptive coefficient, and adaptive coefficient, it varies based on the season. So when this is applied, so you see this and the winter season, the pink color dots, they are from the PMV, and blue dots, they are from the actual field survey data. So there is a deviation. So when this correction factor is applied to the PMV data, they become aligned to the the field data. Same is for summer. There is a deviation. When this corrective term is added, the data align with the field data. So now after that, um, I also studied the residential building stock of Europe. So when I was doing my postdoc, so here I was assigned to study this the residential buildings of Liège city, because there was a plan in the bill, and also the financial incentive was given to the building owners to renovate their buildings, to improve the insulation, and so that the heating energy consumption can be reduced, because Belgium has one of the highest heating energy consumption per meter square. So it is crossing about 230, 250, and the Europe standard is bringing it to, at that time the average Europe standard was around 130 something. So it is almost double of that. So the Belgian government, they wanted to reduce this building heating energy consumption, but their program failed. People did not go for it. So they want to know what is the reason behind it. And so I carried out this study. So to carry out this study, I took their general survey data. So in in the general survey data, it is mandated that every house owner, they should fill an online form and or offline form, whether they will where they will give every detail about the building, like what is the composition of the wall, how old is the house, what kind of window is a single glazing or double glazing, or whether there's a insulation, then what type of insulation, what kind of boilers they are using for hot water circulation in the radiators. So those kind of, and how old is that, what kind of fuel they are using, what is the electricity consumptions, and so on. It's a lot of data they have to put. So I used that database and extracted the data, and I focused on this, the green highlighted neighborhoods. So we can say it's as a ward, and this is the city boundary of Liège city. So it has 27 wards. So I focused on this green highlighted wards, and because they have the highest concentration of old buildings, those buildings that are constructed before 1945. So they're, though there, most of the city was impacted in the First World War and Second World War, but there was a lot of constructions work that happened between First World War and Second World War. So those houses, though they are old, but they are renovated in between during that time. So I focused on this, and then I also did some literature survey, that what is the energy consumption of Belgium with respect to the EU 27 countries, and what sectors they are consuming more, what kind of fuel the households are using. So you see that and the left hand side bottom left hand side figure, that they are using oil products, natural gas a lot. And then what kind of houses, like they have large number of houses which has two facades, they share two facades, and the single houses, they are also in large numbers. So uh, so again, and I also totally segregated all those things, how this historical houses based on age, shared facade, type of fuel they are using. So I segregated everything based on this to generate information. So you see this in this figure, you see that the central part of the city center, the city center, you see that these houses, they have central heating systems. And as we move away from the city center, they have individual, they have individual heating systems. Also the distribution of the houses. So the large number of houses that they lies between 1920 and 1944, because they are constructed between or renovated between that time. And also new construction is very low. Also the city center has the highest number of building that has the shared facade, means almost two side, like a building has four facades in four directions, so two facades it has been shared. So that kind of houses are concentrated in the city center. Then this is obvious because there is a space constraint and their apartment concepts are there. So we have just on the front, on the back side of the building, they are exposed to the air, and rest two directions it has been shared by the other apartments. And also I monitored the the houses, and to know how their heating system is performing. So here I found that this house has a manual control, and since it is a manual control, there is a lot of fluctuation in the heating, indoor temperature, because it's the control is not swift. Whenever they feel it is too hot, they will reduce the heating, and then when they feel it is now cold, they will increase the heating. So that's why we observe a lot of fluctuation in this house. But in the next house, it has a thermostat installed, and it automatically controls. So it has a much smooth temperature profile inside the building. But the problem is that in the month of May and the last week, we see that indoor temperature is crossing around, the bedroom temperature is crossing, going almost close to 30 degrees Celsius. So this is a problem now Europe is facing, because there's a overheating problem in the buildings, because they have recommended large renovations, improving insulation, and the structure of the house is such that you know the bedroom is generally on the top floor. So if it's a two-floor house or three-floor house, the bedroom is will be on the top, and they have a large external facade where there's a glazing. Know that the glazing is double glazing, but it allows sun to come in. And then, and also in summer days, the daytime, the day length is large, so it starts somewhere between 7:30 and it lasts up to evening 7:30 or 8. So at that time they receive sunlight, and so there is a heat overheating, and entire Europe, they are facing this problem. So now they are working on the cooling, affordable cooling technologies, and IEA has they have formed a task force, and so they are looking for affordable cooling technologies for European homes. So this is very strange. And also I found that people, they don't intend to heat or cool the entire building at once at one temperature. So they are they are more focused about the temperature of the living room, because they spent a lot of time in the living room, their kitchen area and everything is attached to that, and bedroom is just used for just for sleeping purpose. So and it's used, its duration is, suppose it's from 10:30 or to 5 in the morning, and they prefer a relatively cooler temperature in the bedroom. And so here it shows that the people prefer different temperatures in different rooms based on their priority. So this was one of my conclusions, that if when we are running a building simulation, we have to give different temperature. We have to define different temperature zones in the same building. We cannot just assume that okay, they will heat or they will cool entire building at particular temperature. So in if we assume that entire building is cooled or entire building is heated at particular temperature, we always tend to overestimate the savings. When we overestimate the savings, we will pass out wrong information to the occupants to take the take the incentive that is offered by the government to renovate their house. So at that time they are calculating that the payback period of this renovation is about 7 to 8 years. But when someone carried out this renovation, then he found that he is not saving that much what he should have been. Just happened This happened because of the wrong assumptions. And then the word of mouth, like it's a spread like this: don't go for this because there will be a burden on you, you will not be able to repay the bank loan, and so many things. And also these buildings, they are constructed between 1922, uh, just before, we can say, 1945. And that time there were no regulations, and there is no insulation. So what happened, all these buildings, the people now still they are functional, still it is being used, and then they have a lot of furnitures in the houses. And now when you apply a insulation, because you have to optimize the cost, when you optimize the cost, you will go for around something about 5-inch or 6-inch insulations. So if you apply 5 or 6-inch insulation, you will lose a lot of space. Now the furnitures that you have installed, that you have in your house, you cannot fit them as per your wish, so you have to discard. So this is also a another other expenditure that was not listed in the payback period calculation. So people, they don't want. And also the stairs, they are very narrow stairs, like if it's a 3-story house, they have a stairs inside the house, and then these stairs are very narrow, and if they put the insulation, it becomes further narrower, and it creates a problem. Now to you know to increase the staircase length or width, they have to do a lot of breaking inside this house, and then they don't want that. And so these are all this expenditure that was not you know accommodated in this payback period. And so people were not going, though people went for improve their glazing, window glazing from single glazing to double glazing, because it was relatively easy to implement. And also the government is giving some the financial intensive incentive in terms of tax rebates that were attractive. So people, no doubt the people go for improving their glazing, windows glazing, but they don't go for improving the insulation, the applying the insulation. No doubt improving the insulation will improve the quality of the environment, so now entire building can be used. And but again, the money, the finances involved, they were too much to bear. So these are my findings, so I told them. So now they are working on it still. These are some of the adaptations that occupants that when they were taking in the buildings. They're switching on and off the room heaters. They are using portable heaters. It shows that their room were not evenly heated. Even if it is a single room, the room was not evenly heated. So they are also they're using warm clothing, moving away from the window, moving to different rooms. And almost all the houses that I surveyed or I monitored, uh, all the occupants, they preferred bit brighter light, so their lighting level is also low. Now I'll share some of my experience about thermal comfort in different built environments. So thermal comfort of in the offices of Northeast India. So this is the typical, Assam type building in Northeast, and this is the typical office environment. And the two pretty women you are seeing here, they are from Shillong, and this is their traditional attire. So I took their permission. So they happily they agreed to you know to pose for a picture, and that's why I'm using it here. And these are the locations. And so I studied Tezpur, offices in Tezpur and offices in Shillong. So one is in warm and humid climate, and one is cold and cloudy climate. So these are the thermal comfort, and these are the instruments. The figure one on the top left, it shows the instruments that we use to record the physical parameters like temperature, humidity, air velocity around the occupant. These are some of the results. So we see that the temperature between 26 to 29, more than 80% of the subjects, they found themselves comfortable. And comfort temperature, it comes at about 27.2 degrees Celsius. Uh, but the preferred temperature is comes out to be 24 degrees Celsius. This is how it's and also we plotted the, because most of the offices were naturally ventilated, so they don't have AC installed. So we also we tried to find a relation between fan use and temperature. So we found that when temperature is almost 32 degrees Celsius, almost 70% of the fans, they were running in the offices. Also this the clothing pattern is non-linear. This behavior is non-linear. So uh, this is obvious because the particular clothing level we have to maintain what is how much with the high temperature. So it's the office decorum. So people were, they can't decrease their clothing level below that. So there is a type of adaptation going on. And also the preferred temperature is almost 24 degrees Celsius. So people, they want to 24 degrees Celsius, but they are comfortable. Comfort temperature is 27.2 degrees Celsius. So study in academic classrooms. This is the typical, this study is done in Jaipur. It is hot and dry climate. It lies in the composite climate of India. And this is this is the study done with almost 2,400 sample size. And then we find that ASRE comfort boundaries, they do not define the comfort. So what we did is that we used all our data to define new comfort boundaries for composite climate of India. So this is so this defines the comfort boundaries, and this we proposed in our publication. Here also we find the preferred temperature in the classrooms. It's about 26.4 degrees Celsius, and almost around this around 22 to 30.5 degrees Celsius, almost more than 80% of the students, they feel comfortable. And no doubt this temperature is high, very high, but the students, they don't have option to use AC, air conditioners, and all these classrooms were naturally ventilated. So we see relatively higher comfort reporting in this from the students. This is about the status of the thermal comfort research in classrooms. Still, there are very few studies done. So total till date now about 180 articles, only 180 articles that have reported and that have done a study on the classroom thermal comfort. And this area is very important because, mm, classroom comfort, it affects the ability to learn, the students' ability to learn, and also the classrooms, you know, mostly these are controlled by the faculty members, like teachers. They come and then they will regulate. So, this is the case, and this is the breakup. So this study was published in 2019, so it's a bit old, but at that time that was the status. So very few research articles were published on this. So here, this plot is very interesting. It says that the university students, they are very much sensitive to the change in temperature of the classrooms, and least sensitive were the nursery or primary school students. And this the reason behind it is that the nursery students, they cannot express their their thermal feeling, and generally their dressing and the temperature control of the room, they have to be dependent on the teachers, or the clothing has to be done according to the parents. So this was the main reason. But for university students, they can express their feeling, and they have some amount of control on the on the devices that impacts the indoor environment, like switching on fans, controlling the speed of fans, then switching on and off AC if there is an AC, or opening and closing of windows. So these kind of controls are available, and the university students, they can use this effectively to control. So they are very much sensitive to the change in the environment, in the classroom temperature. This shows about the range of the comfort temperature that has been reported in the literature. Again, the university classrooms, they have much higher range. Then thermal comfort status in industrial buildings. Same, we studied this in Jaipur building. And this study we carried out during the COVID time. So what is the impact of using mask and sanitizers? And so we also tried to cover this and the occupants view. So this shows about the range of the temperature that people, they have reported comfortable. So no doubt this 35, almost 35 degrees Celsius, this is very high. But this is the industrial environment where they use lot of high velocity fans, so there is some kind of compensation there with the with the high wind velocity. And in this range, more than 80% of the people, they were reported themselves comfortable. Again, this is the clothing pattern. Again, it's a non-linear behavior um, with respect to the outdoor temperature. And here the workers, they say that the using of face mask, they found it irritating, they found it suffocating. Also, they reported bad odors, difficulty in doing work. So these are some of the major factors the the people faced when they used face mask while doing their work in industrial environment. And this is about our uh, ASRE comfort database MK2, where our result got like the data from our study, they are all incorporated there. So these are the, this is highlighted. So that's all from my side. Hello. Hello.
Yes, sir.
Yeah. So I just completed
Yeah.
my presentation.
Yes. Yes.
Yeah.
And now it is for the audience. Very important presentation, because we have already discussed energy saved is also energy generated. So a lot of energy saving technologies for the room conditioning, climate conditioning. Please raise your queries or your comments. Yes, audience, you can speak also. Don't just keep on writing. Mr. Mohammad Afzal. Yes, try to speak also. Ajay Chiller. It is a platform we have to interact.
Yeah.
Yeah. Because of the pandemic, we are not meeting physically, but
Yeah.
in virtual mode also, we our technology has enabled us to express our feelings or our queries. Please. Yes, all students. So many, some of the students also joined this course.
Yeah. So actually, this is about something different. But here, there's in this area, a lot of research is going on, and it has actually a direct implication on this, like energy building functioning and building conditions like indoor environment quality. So any one of you who will work in this area, they will come up with this
It is
term
very,
like
very
thermal
essential,
comfort.
sir. Very, very important. The government also looking for 100 smart cities. And whenever we are going for the design of new cities or new buildings, we must this take into this into account, so that we can reduce our energy liability.
Mm.
With proper planning, as you have already mentioned, more than around 30, 30, 35% cases, in many cases, energy can be saved. So that
Yeah.
is another way of alternative development, or we can say that is an alternative energy
Mm.
we are creating.
Yeah.
A lot of carbon footprint will be reduced due to this. And we have already discussed that we are facing a lot of climatic problems. And there are some countries like Maldives, etc., they are facing threat to their existence.
Yeah.
And if we, all over the world, if all environmental engineers as well as civil engineers will look into this matter, then in future we will find definitely we will be able to control the climatic temperature.
Yeah.
Yes, please, any of my students? Ankit,
Yes, sir.
yeah,
Yeah.
about the lecture.
Yes, sir, sir. Can
Very
you please
very
explain
also.
about the thermal occupancy, means thermal comfort of enabling that? That kind of means thermal comfort. What kind of thermal comfort we will get?
Yes, the thermal comfort actually it depends upon the occupants. Occupants, like every like if in a room we have faced some like situation, like at some time you said that okay, I am feeling very hot, but some of your friends at the for the same environment they said that no, I am okay. You might have faced, and like in your student life also, or at your
Yes,
home
sir.
also, where you are saying that okay, now I need to switch on the fan, but your parents or some other person in the same room, it was said no, don't switch on. And if switch on also, put it on the low speed, low rpm, so that the air velocity can be reduced. This is the actually challenge to the engineers that are, or scientists, they are working in this field, because you know it varies from person to person. In the same environment, one person say that I am comfortable, other one will say no, I am not comfortable, or I am slightly comfortable, or someone will say I am feeling too hot. So this, and here what we have to do, that we have to take everyone's view, and then we have to converge this to some value, where we can say that okay, if we put the temperature, humidity and air velocity of room at this level, in this range, almost 80% of the people who are occupying this space, they will report comfortable. So there are different kind of statistical techniques that we use,
Okay.
and we converge this data to this range, comfortable range, and outside that it's all uncomfortable. So uh, so here like since you have experience, so this this is the critical thing. And also when you are designing the building, this kind of data is important. So if you are designing for, suppose, in a old age home. So
Yes, sir.
in a old age home, our study says that people, they need a bit brighter light. They are sensitive to temperature. They are comfortable at bit higher temperature compared to the people who are in young age. Like young age means like um, in between 30 to 50 years of age. People, they are comfortable at lower temperature, but people, they're in old age home more than 60 years, they they feel comfortable at higher temperature.
Yes, sir.
Also in case of women and men of same age, women feel you know comfortable at bit higher temperature compared to men.
Yes, sir.
So for them also the temperature tends to bit higher. They will report, when we analyze the data, there is a difference of 1 degree or 1.5 degree in the temperature. So that kind of things is becomes very uh, crucial when you are designing a building. And that too, when you are designing a HVAC system for that building. So a slight misinformation will lead to a huge amount of energy consumption, because in Hong Kong, if we go, and the Singapore and Singapore, it is a tropical country,
Yes, sir.
where temperature always tends to be at about 32 degrees Celsius. And
Mhm.
if you go inside the offices, you will feel too cold, because temperature is maintained at around 21-22 degrees Celsius. So in this summer condition, people are wearing woolen jackets and coat, pant, there's heavy clothing. If they come in just, they cannot survive the office environment if they wear just shirt, simple cotton shirt. So there now a lot of emphasis is being given that okay, now we have to increase the set point for cooling. Now they have recommended that set point temperature should not be below 24 degrees Celsius. So
Yes,
this
sir.
2 degrees Celsius, you see, if it's the 20,000 square meter office, how much energy will be saved in this 2 degree, you know,
Yes, sir. Yes, sir.
higher set temperature.
Yes, sir. So definitely everyone remarks is responsible for assigning the temperature of the uh, room or the hall or office
Yeah,
space.
everyone view is very important. So we take everyone's view and we carry out some statistical analysis to converge this data, and
Ye-
then we come up with certain values where we say that if temperature is kept between this range, 80% of the population inside that room or built environment will be comfortable.
Yes, sir. So like in Hong, you have told about Hong Kong case or Singapore case. Why don't we maximize the temperature? Like why won't we increase the temperature to 24 degrees Celsius? Why it is for 21 degrees Celsius? Why can't it is very simple method. We can increase temperature to 24 degrees Celsius.
No, you cannot do abruptly. You
Okay.
cannot do abruptly because there's a people requirement, people adaptation is there. Some people who is coming from the
Oh, yes, sir.
colder countries to work in, because these are also there are offices where the people from different countries they work there. So someone from the tropical country, for him 27 28 degrees says hey, he is comfortable. But if you put a, anyone from Nordic countries like Finland, Denmark in this 27 28 degrees Celsius, he will just die. That he will say that, oh, this is unbearable hot.
Yes, sir. Yes, sir.
There is
So
another problem of optimization.
yeah, so we cannot just abruptly increase or decrease.
Yes, sir. Definitely,
So
sir.
yeah, so we have to do a large sample survey, and then in the same building, then we have to analyze their working conditions. If their high metabolic rate, then their sweating will be high. If someone's job is just walking and moving here and there, then he will emit lot of heat from his body.
Yes, sir.
And then if someone has a just sitting job, like he just sits, he come in the office and sits there, he very rarely
Mm-hmm.
moves, then he will emit very less heat from his body. His metabolic activity is low. So
Mm-hmm.
for him the requirement will be different. The person who is doing like moving just here to here and there, then his requirement will be different. So all these has to be optimized, and then we have to use, like that's what I told, statistical techniques are there where we use it and we try to converge this or everything to these 3 4 variables, and we just try to find the range when each where more than 80% of the people they report themselves comfortable. And 80% is why we focused on 80%, because most of the time, like almost 75 to 80% of the time, the occupancy in that particular space will be 80%.
Yes, sir.
Very few hours out of 8 hours, half an hour or 1 hour, there will be 100% occupancy. But
Mm-hmm.
almost 6 to 7 hours you will find that occupancy is close to 80%.
Yes, sir.
So that way we meet the criteria.
Okay, sir.
Yeah.
Thank you, sir. Thanks a lot, sir.
Welcome.
Yeah, very good evening, sir. This is
Yeah,
Afzal.
yeah,
I'm
yeah,
sorry.
okay.
Actually, I went for namaz. I'm sorry for that.
Yes, yes, yes.
But I was on throughout in the whole session.
Mm,
Firstly, I would like to thank you, sir, for delivering such an informative and very elaborative session, sir. Thank you
mm,
so much, sir. If I got your lecture correctly, then I have a question, sir.
yeah,
As you told that you gave an example that when the employees of any organization enter to the building,
mm,
they switch on the AC at 22 degrees centigrade,
yeah,
and as the time goes on, then temperature also goes on rising, and
yeah,
at the noon time it goes to 26 degree.
yeah,
Then at this point I have a confidence that when the there is a crowd more number of employees are there. There are some workout. There are lots of system going on. Metabolism. That's why there is energy, heat energy going to generate. So instead of lowering the temperature, why they are going to increase the temperature and they feel comfort
No,
at 26
no,
degrees centigrade?
yeah. So it is actually it is because we have certain like every system, like if you are working on a computer, though, then every computer it emits some kind of heat while it's
Ye-
running. So while designing HBSE, we have to consider this, the heat emitted by this system, that system, lot of things.
Okay, okay, sir.
But
Yes.
here we are sorry, we are considering about the occupants. So it is there are a lot of study here it is done. Then when we move from like in a transient state,
Yes, sir.
like suppose I am moving from different environment to different environment, the time to adjust to that environment, present environment, is
Yes, sir.
minimum 20 minutes. Minimum 20 minutes. We
Okay,
have
sir.
to provide a person minimum 20 minutes. Uh, take an example of yourself. So when you enter from outside, when it is very hot, to an air conditioning room, though it is running at 22 degrees Celsius,
Yes,
you
sir.
want that you should be cooled immediately. So you will just reduce it to 18 degrees Celsius. I mean 18 degrees set point,
Yes,
the
sir. Yes, sir.
minimum set point provided to your cooling system.
Mhm.
And then after some time, after 20-30 minutes, when you tend to feel cold, you will again start increasing your set temperature. Now you'll make it to 22. Even if you are directly on the blower side, facing the blower,
Yes, sir.
cold wind, you will again increase. So
Okay.
yeah,
So
so
it means that
this
the
is the
initial.
logic. This is the logic. And
Okay.
also we are uh, there is I have just talked about the personal uh, personal comfort devices,
Yes, sir.
where at every person desk, like there will be some kind of blower and some return air, like it can
Mhm.
suck the air from there. So this kind of research is also going on, but this is very complex thing to design such a system. But here this was an experiment done in Sydney in summer month. And the people, all the people, they have been provided with a ipad like online device, where they have to just click on the screen. A
Yes, sir.
button is provided where they are comfortable, they're not comfortable, they're comfortable, they're not comfortable. Like every 20 minutes it will pop up a small on the things, and then you have to say comfortable and not comfortable. And there are sensors placed all around, and they will record this temperature. And then online analysis were going on with this. All this, the programs, online programs were developed, and it is calculating, and then it is giving the feedback that if we put this temperature, 80% of the people will be comfortable. So this temperature, what we got from this program, it is fed to the HBSE system. And then over a month, a general trend was observed that this set point goes on increasing, and at noon it attains the maximum. And if we keep at that, and then corresponding, what is the energy consumption of the building for cooling, they found that if we keep this, up to 30 to 35% lower energy consumption is reported for cooling. And this is also according to what we do in our thermal comfort study, we find this. So this is the general trend, and what a person does when he moves from one environment to other environment, he needs minimum 20 minutes time to get adjusted.
Okay, sir.
So yeah.
So, and your last slide, somewhat last slide, that the comfort study on the basis of classroom, that is
Yeah.
very much interactive, sir. I am interested to work onto that.
Okay.
At current, the due to the corona pandemic, the classes are off. But as soon as these are recovered, then I would like to get in touch with you and to work with this, sir.
Yeah. Okay. Sure. I'm ready.
Yeah,
You can get in touch with me.
sure, sir.
I'll be
Thank you.
happy to assist you. Yeah.
Thank you so much, sir.